Hello everyone, good morning to you all. So, today we'll be looking at section 1.3 decimal expansion of real numbers. So, in last class we learned what is a rational number. So, rational numbers are those numbers that can be written in the form p by q, where p and q are integers and q is not equal to 0. So, examples were 1 by 2 2020, because 2020 can be written as 2020 by 1. Negative 5 can be written as negative 5 by 1. So all those are rational numbers. Now irrational numbers are those numbers which cannot be represented as in the p by q form. An example that we saw was root 2 and pi. So rational numbers and irrational numbers are together called as real numbers. So this is what all that we learned in the previous class. So next we make an attempt to classify the numbers as rational numbers and irrational numbers based on their decimal expansion. So last class, how we classified the numbers as rational and irrational, we classified it based on whether we can write it as a p by q form. If we could write it in the form of a p by q, we would call it a rational number. If we could not express it in a p by q form, we would call it as an irrational number. So now in this class we'll be looking at how to say whether a given number is a rational number or an irrational number by looking at its decimal expansion. So we know that 1 can be written in the decimal form as 1.0. So negative 5 can be written in decimal form as negative 5.0. So how do we write 1 by 2 in decimal form? Let us recollect. So we divide 1 by 2. So first we have 0 times, the remainder is 1. Then we bring down another 0 after putting the decimal point. So this is all we are recollecting what we have done in lower classes. So remainder is 1. Now when we bring down the 0, 2 multiplied by 5 times gives 10, and remainder is 0. So 1 by 2 is 0.5. Okay, so now let us look at 5 by 4. So 5 by 4 goes 1 times, 4 minus 4, the remainder is 1. So we are trying to convert it into the decimal form. So we add the decimal point, we bring down the another 0, we have 10, 4 times, 2 times, 4 is 8, so remainder is again 2, which means we can still move on, still carry on. So we bring in one more 0, so 5 times 4 is 20, so 20, and our remainder is 0. So 5 by 4 is 1.25. Okay, now let us look at 1 by 7. So 1 by 7 is 0 times, we get the remainder 1. Next again we bring a 0, 10, 1 times, 3, remainder 3. Then again we bring one more 0, 30, 28, remainder 2. Then we bring another 0. I think I missed one step in the middle. Okay, so remainder 2. Then we bring down another 0, so remainder 20. 2 times we get 14, remainder 6, remainder 6. Then we bring down a 0, 60. So 8 times 56 minus 4, again 40, remainder 4, we bring down another 0, 35, remainder 5, remainder 5, we bring down one more 0, 57 times 7 is 49, remainder 1. Again we can keep on going. So we have 10, 1 times 7 is 7, So we have 3, again 30, 4 times 7 is 28, 2. So this keeps on going. So it is 1, 4, 2, 8, 5, 7. So I leave the rest to you. Try finding out. Can you see whether some pattern is occurring in the decimal expansion? So 1 by 7 we get 0.14285714, and this keeps on going. So now let us look at another example. Let us try 1 by 3. So 1 by 3, so 3 0 times 1, again remainder 1. We bring down 1 0 after putting the decimal point. 3 times 3 would be 9. Again remainder is 1. We bring again a 0 down. Again 3 times 3 is 9. So even this also keeps going on. So for p by q rational numbers, in the first two examples, that is for 1 by 2, we saw for 1 by 2 we saw that our remainder becomes 0 and we get decimal expansion as 0.5. So the digits stop after the decimal point, so they come to a stop. Now for 4 by 5 we saw the remainder becomes 0 and the number of digits after the decimal places, they also stop. In the third case we saw that this does not stop, it keeps on going, and the remainder also does not become 0, this keeps on going. And the same thing we saw in the fourth case, 1 by 3, we see that the remainder never becomes 0 and the decimal expansion, it keeps on going. So we saw 1 by 2, its decimal expansion was 0.5, the remainders were 1 and 0. Then we saw 5 by 4, decimal expansion was 1.25, the remainders were 1, 2 and 0. Then we saw 1 by 7, which is 0.1428571, and the remainders were 1, 2, 3, 6, and so on. So I would like you to try a few more examples like these. Note down their decimal expansion and note down their remainders, as in this order, the remainders that come. So I would like you to try a few more examples. Kindly pause the video here if you are fine with it, and try to find out if there is some pattern that you can see in the remainders or in the decimal expansion of these rational numbers. If you find something repeating or some kuch ajeeb jaise, something in the decimal expansions or in the remainder. So pause the video here, and if you can try to find out something happening or some pattern in these two, in the decimal expansion and in the remainders, that will be appreciable. Okay, so if you could not find any pattern, then it's fine, it's completely okay. Let us together look what it is. So we saw that the remainder either becomes 0 or it starts repeating after a certain stage. So either it becomes 1, say in the first case 1 by 2, the remainder became 0. Second case it becomes 0. So either it becomes 0 or the remainder start to repeat. Let's say 1, 3, 2, 6, 4, 5. Again the same thing, it starts to repeat 1, 3, 2, 6. So in the case of 1 by 3 we saw that after the first place itself the remainders start to repeat, but in the case of 1 by 7, after 1, 2, 3, 4, 5, 6, only after 6 remainders did we get a repeating pattern. So the remainders, they either become 0 or they start repeating after a certain stage. Then what we can see is the decimal expansion stops or it starts repeating. So the decimal expansion stops or it starts repeating. Here we can see 142857157, then again 1428571 again. So the next will be 1428571, and this keeps on going. Here we see that 3 is getting repeated. So the decimal expansion, it either comes to a stop or it starts repeating. So, and if the remainder becomes 0, the decimal expansion stops. If the remainder starts repeating, the decimal expansion also starts repeating. So if the remainder becomes 0, the decimal expansion stops. If the remainder starts repeating, or if the remainder does not become 0, which means our decimal expansion also is not going to become 0, and it will also repeat. So if the remainder becomes 0, decimal expansion stops. If the remainder does not become 0, that means it will start repeating. If the remainder starts repeating, the decimal expansion also starts to repeat. This is an interesting fact. The number of digits repeating in the quotient and the number of remainders repeating is less than the value of the divisor. So let's see here, 1 2 3 4 5 6 6 digits are repeating in the decimal expansion. 1 2 3 4 5 6 6 remainders are repeating in total. So after every 6 remainder, the 7th remainder is again the same as the first one. So we see that there are, and the number of repeating digits and the number of repeating remainders is less than the value of the divisor, which is 7. See here, only one number is repeating, only one remainder is repeating, and it is less than the number of repeating remainders, or the number of repeating digits is less than the value of the divisor. Here the value of the divisor is 3. Here the value of the divisor was 7. So I would like you to try more examples on your own. See if all these properties are true, whether you can find any example where any of these properties not correct, something is giving a false output. So I will encourage you to try more examples. So we saw that in cases 1 and 2, the decimal expansion, it terminates or ends after a finite number of steps. So we call such a decimal expansion as a terminating decimal expansion. So if the decimal expansion stops, as we saw in the case of 1 by 2.5, you see the decimal expansion stopping. For 5 by 4, the decimal expansion stops. So such a decimal expansion is what we call as a terminating decimal expansion. However, in the case of 1 by 7 and 1 by 3, we see that the decimal expansion does not stop. So we call it non-terminating. So if it stops, we call it terminating. If it does not stop, we call it non-terminating. We also see that it starts recurring. So recurring means repeating. Recurring का मतलब है repeating. So such a decimal expansion is called non-terminating recurring. Non-terminating because it does not stops. Recurring because we can see then the digits in the decimal expansion starts to repeat. Okay, so thus we can see that we see that the decimal expansion of rational numbers. So अगर आप कोई भी rational number देखें तो the rational numbers, the decimal expansion of rational numbers have two choices. Either they are terminating, okay, either they are terminating और they are non-terminating recurring. इसका कोई अंत नहीं होता है और after a certain number of stage ये repeat भी करता है. So they have only two choices. Either they are terminating or they are non-terminating recurring. Okay.